Hello. We are going to go over the answers to ChemQuest 5, the numbers in chemistry ChemQuest. This was talking initially about the difference between qualitative and quantitative. And number 1 asks, what is the difference between qualitative and quantitative observations? Again, qualitative, hopefully you see the word quality in it. Qualitative refers to a general quality of a characteristic like tall, short, long, wide, etc. Whereas quantitative includes the quantity of the characteristic, how tall, how short, how long, how wide, etc. Therefore, quantitative observations will always contain a number to specify more precisely than qualitative. So again, we see the word quantity, which means that we have a number, and we also should have always a unit. In science, numbers don't make a lot of sense if there is not a unit on it. Question number 2 asks you to write an example of a quantitative observation that you may make at home or at school. There are lots of them if you think about what you've done since you got up this morning. Any of these would be examples. I like to eat 2 bowls of cereal each day. My shoes are size 10. I drove 5 miles to school. Anything like that that involves a number would work as a quantitative observation. Question number 3, why are instruments such as rulers, scales, balances, thermometers, etc. necessary? It's because the instruments help us to communicate with each other effectively. Without instruments, we could only speak in generalities. They also make it possible to know exact quantities. So there's a story about where foot may have originally come from, that it started as the measurement of the king's foot. However, that's not very useful because unless your foot is exactly that same size, you can't measure things. So that's why a meter is the same everywhere in the world. It allows us to make measurements and to verify those measurements in other places. And when we talk about a meter or a gram or any of the metric system values, everybody around the world knows what we're talking about. Next, you see something about units and talking about the SI units and their common prefixes. And the metric ones, length, mass, time, temperature, volume, amount of substance. So they give you some prefixes. Again, I like mine, the mega. King Henry died by drinking chocolate milk. Okay, and again, I like it up and down because it allows us to not just move our decimal, because again, we don't want to do that anymore. So if we look at question number 4, question 4 asks us, how many milligrams are there in 1 kilogram? So this is saying 1, so this is asking us that in 1 kilogram, how many milligrams are there? Okay, so again, we're going to use dimensional analysis, which is basically using algebra. So our idea here is we're always going to start with our given. Okay, so we start with 1 kilogram. And those equalities that we talked about the other day. So this idea is like algebra, where you have an A, B, divided by an A, and because we have an A on a top and a bottom, our answer becomes B. So this is the same kind of idea. If you need to, you can think about it being over 1. Kilograms are in our numerator, so I need kilograms to be in our denominator. And I'm trying to go to milligrams, which is going to go in our numerator now. So kilograms, we're treating our units like they're algebraic letters, and we're crossing them out. So this is going to give us an answer in milligrams. So the question here then is about which one's larger. So when we look at this again, we're talking about kilo here and milli. And so kilo is bigger. So again, we make our larger one equal to 1. And then we count to figure out how many we need. So we have 1, 2, 3, 4, 5, 6. So we can write this as 10 to the 6th. The other way, if you prefer, is you could write this instead as a 1 with 6 zeros. So 1 million. So obviously 1 times 10 to the 6th is, okay, 1 million milligrams. So that is how we would do this. Again, I'm very, very picky. I know that in middle school you learn to do this just by moving the decimal place. However, you were moving the decimal place to the right because you were multiplying by a number. We know we're multiplying by the number because the number is in the numerator. If the number was in the denominator, we would be dividing by it. I know this is simple math. What's important here is that you're able to set up this problem correctly, because eventually we won't be working with such simple numbers and it won't be so easy to figure out the math. Our second question, number 5, says 21.5 kilometers, and we want to know how many meters that is. So again, this is our given, so we're going to start with 21.5 kilometers.
Who are you talking to?
I'm talking, you don't want to talk right now because you're going to be on my recording. So, kilometers are in the numerator, so they need to go in the denominator. And again, I'm looking to go to meters because that's the unit I'm trying to change to. So again, I go back to my metric system, right? And this time, again, we're starting with kilometers. We want to go from kilometers and we want to go to meters, which is the base. So again, a kilometer is larger, and it's, when you count and look at that, it's 10 to the 3rd, or 1,000 meters. So our answer is 21,500 meters. Again, we crossed off our units like they're algebraic letters. That's how we know that we're in the units that we want to be in. And so our answer is 21,500 meters. Again, this is what your work should look like. If that's not the work you have on your paper, I'd really like you to change it. Number 6 asks, is it possible to answer this question? How many milligrams are in 1 kilometer? And explain. Milligrams, that's a gram, that's a unit of mass, and kilometers is a meter, it's a unit of length. So no, you couldn't answer that question because they're different units of measure. Number 7 asks, what is the difference between a capital M, and a lowercase m? So we're talking about this versus this. So again, this, remember, is the prefix for mega, so this is a mega meter. This is a millimeter. Okay, they are not the same thing. It asks which one is larger, a megameter or a millimeter. This is larger because, again, on our metric system, this is the larger unit. It's at, again, the top here. Here's our mega. All right, the next section was about scientific notation. Again, we use this to write really large and really small numbers. So we use scientific notation to talk about really large and really small numbers. Question number 8 asks, 2 of the following 6 numbers are written incorrectly. Circle the 2 that are incorrect. The problem here is that the coefficient, so this has to be, this is called the coefficient. Okay, our coefficient has to be greater than 1 but less than 10. So letter A is okay because 3.57 is greater than 1 but less than 10. Letter B, 4.23, is okay because, again, greater than 1, less than 10. Letter C isn't because 75 0.3 times 10 to the second, okay, which really is the number 7,530. Okay, this coefficient isn't proper. It's not greater than 1 but less than 10. The correct way to write that would be 7.53 times 10 to the third. That would make it correct. Letter D is okay, 2.92, because again, greater than 1, less than 10. Letter E is not okay. So again, here we have 3 zeros, 3, 5, 4 times 10 to the 14th. 7, 8, 9, 10, 11, 12, 13, 14. So that's really what that number looks like. So again, in proper scientific notation, this is not equal to or greater than 1, but less than 10. So this would really need to be 3.54 times 10 to the 10th instead. And then it would be a number in proper scientific notation. Letter F, 9.1 times 10 to the 4th is okay because, again, it is in proper scientific notation. It's greater than 1 but less than 10. What do you think is wrong with the two numbers you circled? Again, it's that the coefficient, okay, is not greater than 1 but less than 10. Number 9 asks you to write the following numbers in scientific notation. Letter A, you should have gotten 2.531 times 10 to the 16th. And letter B, you should have gotten 3.018 times 10 to the negative 9th. Again, small numbers have negative exponents, large numbers have positive exponents. Number 10, write the following scientific numbers in regular notation. So letter A would be a decimal, and then 2, 4, 6 zeros, and then an 8, 4, 1. And letter B, okay, would be 321,500,000 in regular notation. In terms of the multiplying and dividing using scientific notation, I don't really care if you remember about the adding and subtracting exponents. What's important to me is that you can put those numbers into your calculator and get the correct answer. So again, remember we talked the other day about the E button. So number 11, letter A, you would put into your calculator is 4.6 E34 times 7.9 E negative 21. Okay. When you put that in your calculator that way, you should get an answer of 3.634 times 10 to the 14th power. Letter B, if you use that E button, you would put into your calculator as 1.24 E12 times 3.31 E, okay, E, okay, the 20, and again you should end up with 4.1 times 10 to the 32nd power. For number 12, when you put those into your calculator, again it would be 8.4 E negative 5 divided by 4.1 E17. And again, when you do that, you should end up with 2.05 times 10 to the negative 22nd. And for letter B, 5.4 E32 divided by 7.3 E14. And you should get an answer of 7.4 E times 10 to the 17th power. Same thing when you add and subtract using scientific notation. It's not important to me whether you can do it on paper. What's important is that you can put it into your calculator. For 13A, you should have gotten an answer of 2.525 times 10 to the 14th, so that was 14 or 13a. For 13b, you should have gotten 6.1 times 10 to the negative 18th power. And finally, for 13c, you should have gotten 2.51 times 10 to the negative 33rd power. So those are the corrections and going over ChemQuest number 5, which was titled Numbers in Chemistry.